Good day, and welcome to CFE Media's Virtual Training Week. For this session on game-changing innovations that drive digital transformation, we'll be joined by Thomas J. Burke, Global Director of Industry Standards at Mitsubishi Electric Automation, and Jim DeRocher, President of Data Acuity, Inc. I'm Kevin Parker, an editor with CFE Media and Technology. Following our presentation, be sure and stay tuned for a live on Zoom that will begin at 2:45 p.m. Central. Today's presentation can provide continuing education credits. CFE Media has met the standards and requirements of the Registered Continuing Education Program. Credit earned on completion of this program will be reported to recep.net. A certificate of completion will be available for each participant to download upon successful completion of a test at the end of the presentation. As such, it does not include content that may be deemed or construed to be an approval or endorsement by RECEP. This virtual class session is designed for technicians, engineers, and managers who want to better understand how operations technology and information technology are evolving together to achieve the digital enterprise, including the infrastructure, applications, and technology standards involved. You see before you the learning objectives of today's session. Here are some tips to help you get the most from today's webcast. The exam will be posted on CFE Media websites with the on-demand version of this webcast. The exam is for one RECEP ASEC Certified Professional Development Hour. Before turning to our presenters, we'd like to share a brief video from our sponsor. Please launch the video.
Iconix has been a trusted leader in the automation software industry for over 34 years, helping companies all over the globe to automate, monitor, and optimize their most critical assets. Now more than ever, automation and digital transformation is something organizations need to do to survive and thrive. Businesses cannot simply go on as they were operating. They must future-proof against further disruption by adopting the right technology and embracing the convergence of IT and OT. Join us on October 15th for Connect 2020 Virtual to learn how. This virtual conference will address the challenges we currently face and how to solve and prevent them with digital transformation solutions for the new normal and the decade to come. Experience Connect 2020 to discover how augmented reality, IoT, analytics, and remote expert solutions will all play a key role in helping you master this new reality. Register today at iconix.com/connect2020.
Welcome back. I'd now like to introduce today's speakers, Jim DeRocher and Thomas J. Burke. Jim DeRocher is president of Data Acuity, headquartered in Hampton, New Hampshire. Jim has more than 30 years of automation software experience and is recognized as an expert in systems integration of complex automation systems with data architectures. Data Acuity is an automation software company that focuses on manufacturing efficiency, energy efficiency, and efficient delivery of services for automated systems. Data Acuity is celebrating its 15th anniversary in 2020. Prior to joining Data Acuity, Jim worked at Iconix Software, Schneider Electric, Standard Electric, and TVC Systems. Jim holds a bachelor's in electrical engineering from University in Boston. We'll also be joined by Thomas J. Burke. Thomas is Global Director of Industry Standards at Mitsubishi Electric Automation and Director of Strategic Marketing at Iconix. He is a founding member and officer of the OPC Foundation, where he was president and executive director until November of 2018. Thomas received a bachelor's degree in mathematics from John Carroll University and a master's degree in computer engineering from the University of Data. Thanks, Thomas, for joining us for today's session. The floor is yours.
Hello, everyone. My name's Thomas Burke, and thank you, Kevin, for the great introduction on what we're trying to do today with talking about the game-changing innovations that really drive the digital transformation. I've been involved in a lot of exciting products over the year and projects over the year, and the importance of industry standards and everything going on in the world of the industrial revolution and everything that we are doing to drive the digital transformation has become so important to the suppliers and the end users. What I'd like to quickly, briefly talk a little bit about is this whole thing about what is the digital transformation and what does that mean? Well, from the overall perspective, there are basically 6 stages of the digital transformation, depending on who you talk to. Things like business as usual, being involved in, basically present and active, taking a formalized approach to different things, taking a strategic approach, and really trying to converge and manage all of your things together, and ultimately leveraging, basically being adaptive and supporting innovative learning. So I think what you'll find out is, as you go through this and our customers and suppliers think about all these different aspects with respect to the digital transformation, they essentially are looking to build a complete solution-based architecture and leveraging a lot of different products, and the importance of all the products working together and actually having vendors collaborate together is a very important part of the strategy as companies start to think about what does this mean and how do they deploy the digital transformation to successfully enable in their products. One of the biggest challenges, though, with all the end users that I've worked with is essentially what is their expectations. And typically, I like to talk about islands of automation and how they have all these different things around their respective, facilities, and they find that they're very disconnected. They find that there's, as I said, there's disconnected, applications and devices. And, how can they really automate their facility? And, essentially, is it going to help them improve their bottom line? So there's a lot of expectations of the end users when they think about the digital transformation, like, well, what do I do? How am I going to be successful? How am I going to leverage all this wonderful technical innovations from all these different products out there? So as you think about this, I like to talk again about, beyond the digital transformation, I think about manufacturing overall. And we talk about Industry 4.0, it's really important to understand, where did Industry 4.0 come from? I mean, the first revolution was really the Industrial Revolution, which is really very focused at all the mechanical aspects of, the essentially revolution. Then the second stage was really, trying to do a lot more automated things, right? And thinking about assembly lines. The third revolution was my favorite. I was, the beginning parts of this is when we started thinking about, the programmable logic controllers and actually doing a level of automation in discrete and process, essentially, through the ability to have an industrialized computer known as the PLC. The fourth revolution, which is the most important that we've seen, really has the large momentum, is essentially what's going on with Industry 4.0, as well as all the regional equivalents of that. And the aim of Industry 4.0 and the whole industrial revolution is really to achieve a completely smart factory and a self-organized factory. So if I look at Industry 4.0 and all the regional equivalents, there's basically 4 points, design principles that make up Industry 4.0. It's about interconnectivity, it's about information transparency, it's about the ability to have technical assistance, essentially assisting humans in decision-making and problem-solving processes. At the same time, it's about decentralized decisions, allowing, separate cyber-physical systems to make decisions on their own, and essentially to do a significant level of automation as we approach the all IT, OT convergence. So in the factories that we've seen over the years, there's always been the wall between IT and OT. But now IT and OT IT really has needs to get data from OT. And what we're seeing is the whole concept of focusing on what's known as the IT to OT convergence and the ability to take data from OT and to translate that data into useful information into the IT world. So there's a lot of different things that go on in the OT world, essentially from a connection standpoint, gathering the necessary data from all the different devices and all the different applications, and then be able to take that data, analyze the data, and use all these great products that are out there essentially to convert that data into what's the IT people understand to make useful decisions. And the same is true that IT then, after it makes those decisions, can actually push data down into the OT world. I'm pleased to have joined Iconics to really focus on a lot of the things that they've been doing and how Iconics essentially has really been focused at delivering on this whole concept of the Internet of Things. I mean, they think all about this concept of, managing our devices. How do they manage those devices and how do they interact with the cloud? How do they leverage all that data and basically, make it useful information and ultimately be able to get insights on that data and information to make better decisions and really realize the new business value that all this connectivity and data can give us. So there's a lot of core components in the digital transformation. And what we see with a lot of the different products that Iconics is bringing to the table is basically a managed way to access both wired and wirelessly all these different things, and to be able to take those things and be able to gather data out of these things, and working closely with a lot of our solution alliance partners to really publish that data and take that data and make it visible on what we call our any glass architecture, and essentially be able to take all these different things and have useful information. When I turn it over to Jim, he's going to talk a lot about some specific facilities that have actually leveraged these very great products that Iconics brings to the table in support of the technology necessary for the digital transformation. The components of an IoT solution, if you think about this overall from a architecture standpoint, is, essentially I've got my data from the different devices, and there's a lot of different ways to gather data. Obviously, I've been a fan and I started OPC many, many years ago, but in addition to OPC, there's BACnet, there's Modbus, there's databases, there's, web services, there's a lot of different IoT protocols, inclusive of things like, MQTT and AMQP, that actually provide connectivity to the edge platform, essentially to give us the data necessary. And then the IoT edge platform actually having connectivity from both a bidirectional standpoint, then actually pushes that data up into the cloud-based application. And this gives us the capability of essentially starting to think about that data as information. And you see there's a lot of different applications that you can run on that platform that ultimately then the client applications can access that data directly from the cloud base. So you've got a cloud platform. Okay, then you have what's known as the IoT platform. Then I like to think about these end-to-end software systems that span all this physical connection, and that's the IoT solution. And then, of course, I have my IoT application, which essentially are the user components of the IoT solution. So when you're starting to think about how do I do this digital transformation, and how do I capture, and how do I actually work in this world of this magic thing called IoT, you'll see there's very strong components, and how all these components actually interoperate together to give you true data to information integration. And this is a very exciting part of our overall solution. So there are a number of customer use cases that use the OPC UA technology, for example, and I'm going to go just quickly through a couple of these before we turn it over to Jim. So one of the significant ones that I'm pretty excited about is the work that we've been doing with a major oil corporation, and unfortunately I can't say their name, but what they've done is they've actually leveraged all these different components, and using the OPC UA technology, they've been able to take the respective IoT products and the HMI products that Iconics offers and actually be able to grab this data and consume this data such they can push it up to Azure. And this is a very significant part of the component that really allows them to have a complete automated process control system. So when you think about industrial automation, it spans a number of different industries. The other one is there was some work that we've been doing with Singapore, and essentially it's more of what we call the smart nation. And what they've been able to do is really start thinking about, this whole concept of streamlining operation and really looking at how did they do energy savings, essentially by doing central monitoring of all the different assets and having real-time visibility. Again, this is basically leveraging all of these great components and leveraging everything related to IoT and really taking advantage of this whole digital transformation. So with that, what I'd like to do is turn it over to Jim, who's going to go through a customer success story and essentially provide a good application of how we have been using and deploying the digital transformation using both Iconics and Mitsubishi-based products.
Thank you, Tom. Thank you, Kevin. I appreciate the opportunity to be invited today. Again, as mentioned, my name is Jim DeRocher, and I'm with Data Acuity. I'd like to talk a little bit about some specific applications Data Acuity got involved in that use the tool set that Tom has mentioned, specifically in manufacturing efficiency and specifically taking advantage of data analytics to gain efficiency. A number of years ago, I sat down with the engineering manager that ultimately ended up responsible for one of these projects, and we set forth to build a budget request and a scope of work for manufacturing efficiency, data analytics to improve the overall efficiency of a plant that was already pretty state-of-the-art. And when I asked, well, what can we put down as the specific gains that we're going to get out of this budget request, the answer was, we're going to get magical gains. And what this engineering manager meant is, we're not 100% sure what we're going to get out of this. We are going to try to correlate as much data, try to analyze as much data, and see where it leads us, and see what magic will come out of this that will magically make this plant, this already efficient plant, even more efficient. Well, it's kind of hard to put down on a budget request. We're trying to achieve magical gains. So what we really put down is that we're going to build an architecture, build an infrastructure that does the following data correlation, which is going to lead towards answers as to where we're losing efficiency. We're going to leverage that to gain predictive awareness. We're going to predict where are we going given the current trends within this plant, and what do we have to do to become more efficient. And we're going to build an architecture that's very agile, allows us to change, modify, adapt as the data points us in a different direction. So we'll go through a handful of examples. These are all automotive applications at a number of different plants, including the one I just mentioned that has magical gains. So these are all in the automotive industry, but we've applied the same, these examples are all in the automotive industry, but we've applied the same data structure, the same data analytics across many different industries. So if you're not in automotive, this certainly applies across many different industries. The buzzwords manufacturing efficiency and the acronym MES tend to cover a lot of different automation disciplines. It all gets wrapped under buzzwords and acronyms like manufacturing efficiency and MES. This includes OEE, or overall equipment effectiveness, alarm management, asset management, recipe management, product tracking, product genealogy, maintenance tracking, work in process, labor utilization. All of this ends up eventually getting pulled into these kinds of projects where we're analyzing data and looking for efficiency. For today, we're really going to focus on just a handful of those automation disciplines. We're going to start with how we applied OEE, overall equipment effectiveness. And the reason for OEE, just about every project starts with OEE, and we come back to OEE quite often. The reason for that is that's the tool set, that's the measurement that allows us to focus our resources where their greatest need is. We're going to talk a little bit about taking data from things like control systems, material use systems, quality tracking systems, maintenance tracking systems, and not just leaving it as data to be visualized, but in fact bringing it all the way to things like predictive availability, predictive maintenance, predictive quality, predictive material handling, and predictive performance by taking data analytics and bringing it up to predictive awareness. We'll talk about how we did that in some of these projects. Again, we'll start with OEE, overall equipment effectiveness. The concept for OEE and the principles how to apply OEE have been around for a long time. Most of you have probably looked at OEE at some depth. So OEE is availability, performance, and quality as a measurement of how efficient a given piece of equipment is. Availability being defined as the operating time versus the downtime, and operating time happens to be not a 24-hour clock, but in fact, what was the scheduled operating time. Performance is the speed or the quantity of product versus the design rate of a piece of equipment. Again, design rate is a little subject to interpretation, and we'll talk about that in just a second. Quality is good parts versus bad parts. That's pretty straightforward. In the projects that we get involved in, quite often, we've actually added a fourth pillar to OEE, a fourth number to be multiplied in to evaluate the efficiency of a piece of equipment, and that number is material use. This comes in very handy on things like injection molding, metal casting, but it's also very, very handy in the food industry where a certain amount of raw material comes in and a certain amount of packaged material goes out. What happened to the material that was lost in the middle? If we're going to use OEE as a measurement, as a way to keep us focused on loss of efficiency, it's also important to keep into consideration, in addition to keeping high efficiency, we also want to keep low costs. So I can show you some ways of applying things like capital, material, labor, and consumable costs on top of the efficiency. We're not going to spend a lot of time on that today, but it can be worked into the equation. So the point of OEE is to bring our attention to the areas of greatest need of efficiency gains immediately. So if you throw a plant map up, OEE is, in this particular case, OEE is changing the colors of assets or machining centers, in this case, of a given plant. And so our eyes immediately focus on the red machines. These are the machines that are running less efficient than other machines. And we're scoring each individual machine. But if we want, we could actually score lines of equipment, areas of the plant, entire plants as well, to help us focus our resources down to where should we be trying to gain efficiencies. The challenge with OEE, and again, OEE is a concept and a measurement that's been around for quite some time. The challenge that we've seen through experience is that quite often it leads to finger pointings within plants. So for example, I defined availability is actually the scheduled operating time versus the downtime. Well, the question always comes up, well, who is it that determines what the scheduled time was? Production is going to tell you that during break, we shouldn't be scheduled to be running, so don't count that time against us. Maintenance is going to tell you that during preventative maintenance, PMs, changeovers, cleanouts, we shouldn't be counting that as scheduled operating time. Don't count that time against us. Same thing happens on performance. Who is it that determined what the goal was? So here's the speed of the machine versus the ideal or the goal. Was the goal set by the OEM that built the equipment? Was the goal set by the engineering department that certified a set of parameters on that machine? Or was the goal set by the production manager who's taking into consideration things like break time? And then the same thing will happen on quality. Who is it that determines what is scrap? If you take a part out for destructive testing, is that bad quality or was that a good part? It just can't be sold because it was used for destructive testing or for quality samples. So this often causes finger pointing within a plant. Is our OEE score good or bad because we decided to classify time as scheduled time versus unscheduled time? What we recommend instead of a straight OEE formula is to use something called a loss deployment approach. And what a loss deployment approach does for us is it lets us take the lost opportunity to make a sellable product, and we use the data infrastructure within the tools that we talked about to build this, and actually come up with what was the true opportunity to make a product. I could have made 1,000 parts today if I ran all the equipment at 100% and never ran out of material and always had an operator. And then we can take the amount of parts we didn't make. Well, I should have made 1,000, but I only made 800. So there's 200 parts that I'm going to deploy across the reasons I didn't make it. Was it the machine's fault? Was it the process around the machine's fault? Was it because of a required task? Was it an intentional loss? And what I mean by that is machine's fault. Well, that's traditional OEE measurement. The process around the machine, those are the waiting fors. I was waiting for a technician. I was waiting for material. I was waiting for instructions. Required tasks are things like preventative maintenance, clean out, changeover. Intentional losses are things like we're not scheduled to run on a Sunday. We don't have any customer orders. So that allows us to take OEE, which is quality, performance, and availability, and instead start from the point of view of how much product could I have made today in Utopia. So 24/7, always have an operator, always have raw material, but I didn't make that much. I only made 800, not 1,000. So let's show that loss across areas like efficiency lost because of the machine, efficiency lost because of the process around the machine, efficiency lost because of required actions, or efficiency lost because of management. And it allows me to dollarize that, again, using the data structure and using the tools that we've talked about here today. It allows me to assign a dollar value to how much money did we actually lose because we didn't make sellable product because of the machine. How much money did we not make today because we didn't make sellable product because of the process, the waiting force? So taking a loss deployment approach on the projects that we're talking about today has helped us focus very specifically, not just on the machine efficiency, but on where are all of our losses of efficiency within the plant. Here's a typical report that comes out every morning with here's the actual cost, dollar cost of not making a sellable product because of the following loss reasons. And this is going to keep us focused. Okay, so now we're going to move on to, so that's starting with OEE. We always come back to OEE is how do we keep focused? How do we keep our resources spending their time on the reasons why we're losing efficiency? Now let's drill into these 4 other examples of reaching for predictive awareness, not just the presentation of data, not just logging data, but actually using the data to predict where are we going because of the machine properties that are going on right now. To do that, we're going to talk a little bit about this thing called a DIKW model. And this isn't new. This isn't something that Data Acuity came up with. I encourage you to look into the DIKW model a little bit. But following along with the slides that Tom talked about, we start off with today with very cost-effective collection and organization of data throughout our manufacturing plant. And most plants today have ways of taking that data and correlating it so that it becomes information, not just data. So if I take data that was collected and I associate it with an asset, a piece of equipment, it's now information. If I take data that was collected and I associate it with a serial number or a batch number, it's now information. It's not just data, it's now information. Associated with a time frame, a shift, a day, a week, it's now information, not just data. So we want to build data structures using this tool set that allows us to associate the data to make it information. If we take that information and put it in a report, if we apply some kind of sorting or analytics to it, it now becomes knowledge. And that's where most plants are today. You get reports just every morning that take the data that was associated with a given asset or piece of equipment, and it was plotted on a chart and shows up in your inbox every morning as knowledge. This is knowledge of how specific equipment happens to be running. What we want to reach towards, and what we've accomplished on the examples we're about to hit, is wisdom. And that is, let's take that knowledge, those charts, those reports, and let's have either people looking at those charts, or even more importantly, have the system automatically tell us, here's the kinds of things we should be doing in order to improve the performance, the efficiency that's happening within our plant. So all of a sudden, predictive intelligence is going to take the knowledge and turn it into wisdom. There's 2 other words we want to apply to this, besides data to information to knowledge to wisdom. Between knowledge and wisdom, again, this is something that you can read up on. There's something that happens called insight, and that is, today people talk about machine learning and artificial intelligence takes that knowledge, and by analyzing large sums of data, can gain insight as to what caused us to behave the way we did and what should we change to become more efficient. What I encourage people to do before we jump immediately into machine learning and artificial intelligence, which is something that we do work towards and we do apply, but let's start with applying experience. Let's take some of the more experienced engineers, more experienced machine operators, more experienced technicians, and have them apply the insight to us before we even get to applying machine learning and artificial intelligence. And that's how we try to conduct projects. Let's grab as much insight as we can from the people around us and let that guide us towards how we're going to apply the intelligence systems. Then what we want to do is apply OEE to the results. So we want to look at what was the impact of the wisdom we gained that told us how to change what we're doing in order to improve efficiency. So we're going to take data, we're going to turn it into information by correlating it, and we turn the information into knowledge by plotting it, sorting it, organizing it. We're going to turn the knowledge into wisdom by gaining some insight from a history of this data. But then we're going to circle back around and see what was the impact, what was the gain of efficiency, how did our OEE score react because of the wisdom we gained from the system. So of those 4 different predictive awareness we're going to try to look at, here's an example of predictive maintenance. So in this case here, on the bottom you see a line chart. This is time-based data coming out of a piece of equipment, and there's a number of tabs that you can see there a little bit, measurements 1 through 5, 6 through 10, tooling 1 through 5, tooling 6 through 10, where we can look at time-based information. How did the machine actually behave during the production of a given specific part? In the middle of the screen, you see 2 different Gantt charts. One of them shows the machine mode and one shows the production schedule. So the machine mode is, this is live information coming out of this piece of equipment telling us the thing is running, it's idle, it's running, it's idle. Oh, wait a minute, I had a fault. Oh, wait a minute, we stopped for break. So this is giving me live information of the actual function of the machine. So this is event-based data. The stuff on the bottom was time-based data. The production schedule was a database piece of information. We reached into their scheduling system, pulled out the data from their existing scheduling system and applied that. It's still event-based, but it's events that were generated through a scheduling system instead of generated by the PLC. On top of that, we have a mix of events and records that show us things like machine events, quality events, maintenance events, settings events, and staff events. What we're trying to accomplish here is look at a specific event that happened. Let's say it's a quality event, and be able to line up with that event that happened all of the event, time, and record-based data that happened leading up to that bad quality. Or maybe the event was a maintenance event. We greased the bearings on a gantry robot, for example. We might want to look at all of the process information, quality information, staffing information that happened before and after that maintenance event and come to some conclusions. So what we've done is we've synchronized lots of different dissimilar data in order to achieve this knowledge, achieve this understanding of here's what happened before and after a given event, and here's what happened as a result. So the trick on this particular example was synchronizing dissimilar data. We got to take time-based data, event-based data, data that is differential values, data that is burst data coming out of things like injection molding or metal casting, data that is metadata, so a series of information, an array of information associated with a part, or record-based data, images coming out of a vision inspection system, for example, or records coming out of a maintenance CMMS system, for example. So all of this needs to be synchronized into a single point in time so that we can correlate when this event happened on this particular machine, what led up to it and what followed after it, so that we now know how to predict when that event may potentially happen again. So we talked a little bit about data collected from automation systems, from other databases, scheduling systems, CMMS, for example. Some of the data is coming out of operators' heads, technicians' heads. So it's also important to figure out how do we build data structures where we can let people take what they've observed in their head and without having to think much, push 1, 2, 3 buttons and log for us an event that happened that gets correlated with everything else when this event happens, we tend to see high torque on this particular motor. So those are examples of predictive maintenance by correlating dissimilar data using the tool set. Here's an example of predictive performance. So this is reaching into a control system. In this case, it happens to be a PLC, and pulling out of the PLC a phase diagram, or the subsections of the cycle of a piece of machinery. This particular one, if you look at the top right, says that this cycle time, or this takt time for this piece of equipment, this product, was 6 minutes. That 6 minutes was broken down into 35 or 40 different little segments: clamping, door close, tool change, all the way down to unload, wash, and then going into a starved condition waiting for the next part to happen. This is really good information for a control engineer and industrial engineer to learn, how is this machine really working, part by part by part. Here's how it's working. What's even better is if I could take that set of data and compare it to another set of data. So what if I could take that part to part to part timing cycle and compare it to what was the ideal part running on this particular machine? What if I ran part A instead of part B, the blue one instead of the red one? What if I looked at machine 7 instead of machine 8? How do they compare against each other? So we've used the tool set to do this timing diagram and put it into a whole data set 1 and a data set 2, and the result is we can see what the difference is. We can take a look at how the control system is performing data set 1 versus data set 2. What was the mean, max, standard deviation differential between data set 1 and data set 2? We can use that to predict what is our performance going to be when we run the red product instead of the blue product. Can we predict that something different happens? What is our performance going to be when we're running on machine 7 versus machine 8? That helps us change. That's the wisdom we need to change how we operate machines if they're running different products, if they're running with different standard humidity within the plant. The next example I'm going to go through is reaching for predictive quality. So trying to build data sets that are going to predict for us what will the resulting quality of a product be given the parameters. So this example happens to be a metal frame for a seat, again, automotive seat. And the challenge here is there's a whole host of welding robots that assemble this metal structure for a seat. And we want to be able to predict when a given welding robot is starting to drift, when it needs a tip change, a changeover, or if it needs to be realigned. How can we predict that the quality of the product being manufactured might be affected because of the performance of a piece of equipment? And so the way we're doing that is a combination of operator observations, vision system observations, measurements that collect for us information about each and every weld on a given part that happens to be in front of us right now. So we're correlating what is the design of the part that's in front of me, what is the information coming out of the vision system, what did the operator observe by visually inspecting it, and coming up with information about which welds are drifting in the wrong direction, which are the good welds, which are the bad welds. We can then correlate or align our bad welds and good weld information with when was the last time a tip was changed on the weld. What is the experience level of the operator that is doing, that is working that particular line? What is the model number of the part that's running right now? So by correlating the Pareto chart of the worst acting welding robots to other events, maintenance records, experience level of operators, we can predict that if we don't do a tip change on a welding robot within X amount of time, we're going to start making bad product. If we don't educate operators with a little better training, we're going to start making bad product. So we're achieving predictive quality by analyzing the quality and correlating it with other sets of data. Here's another example, similar thing. This happens to be an engine block, and we're looking for things like chips in solder and crack, and in most cases porosity, to figure out, is this a good part or a bad part? And we're looking physically where on the part did it happen. And then again, this is a combination of vision inspection systems, operators, to come up with what was the problem that happened. In this particular case, a lot of the inspection is happening at a completely different plant from where the part was originally die cast. It's being inspected 2 or 3 days later, maybe a week later. So we're correlating the data that went with the actual quality problem over periods of weeks or days across multiple different plants in order to come up with an understanding of when that particular metal part was cast. If we look at the metal temperature, if we look at the biscuit length, or maybe we look at the cycle time of the die closure, we can come up with some predictions that when the metal temperature is X, we start to see the following quality problems in this particular area of the part. When the cycle time of the die closure is Y, we start to see a different kind of problem. We start to see a crack instead of porosity in a different part of the product. So this allows us to predict quality problems by analyzing, when we see a quality problem, what was all of the data that led up to that part over weeks, over different plants. Let's look at all of that information and come to conclusions that when the following scenarios are in place, we're probably going to have cracks in a given part, a given area of the part. We'll talk just very briefly about applying this kind of a concept to a very simple thing, and that is material handling, both the delivery of raw material to manufacturing stations, but also the removal of scrap material from different areas. So once again, by having knowledge of the efficiency of a piece of equipment, what's the how many parts is it making, at what rate, and what's the schedule coming forward, and then comparing that with how often does a fork truck bring new material to that particular line, how often does it pull away finished material, how often does the scrap bin with the metal scrap fill up. So we can compare activity of the material handling department, driving fork trucks, emptying bins, delivering raw material, to the actual production going on within the machines themselves, at what speed, with what quality level. And then we can start to schedule. Instead of having a fork truck just drive around the plant, we're going to tell it that it has to be at machine number 5 within the next 15 minutes. It's going to drop off a bin to be filled up, and it's going to empty out the scrap metal bin. And that allows us to look at multiple equipment and predict that we're going to have conflicts getting the right material to the right place at a specific time given the production schedule in front of us. So we're combining live real-time information on the performance of the machine together with records collected from the material handling department, together with production schedules, to then predict where we're going to have conflicts in getting the right equipment to the right place on time to improve efficiency. So I'm going to finish this with a couple of ideas on best practices for these kinds of projects. Because they do start as typically very small, very simple data collection, overall equipment efficiency monitoring systems, and they quite often grow to include lots and lots of different disciplines of automation. We use the tool set that Tom talked about because it allows us to start very small, cost efficient, and grow to very complex, very powerful data analytic systems. I tend to recommend that people start from the top of the system and work down. As engineers, we like to solve each individual problem as it comes in front of us. We tend to think about what is the PLC, how much I/O do I have, what network is it on. We tend to think about those things first. I recommend we put all of that aside and we start from what is the data we're going to consume? What do the screens look like? What do the reports look like? What are the analytics we're trying to get out of it? What's the predictive awareness we're trying to gain? Start at the very top, and then work our ways down to the network, the I/O, the touch points. So start at, here's what we're trying to get out of it first. It's hard for engineers to think that way because we want to solve the problems at the bottom. But we want to start from the top, define the data consumption, define the predictive analytics, and then move down towards the I/O system second. We want to organize ourselves around subject areas and job roles rather than organizing ourselves around existing tools, existing pieces of software, existing assets. It's much easier to make smart design decisions when you think about subject areas and job roles and not box yourself in a corner because the tool set you're using isn't really designed for that particular functionality. So try to organize the project around the subject area or the roles of the people using the software. It's really good to understand a long-term goal out of projects like this. If we were to put in all of the predictive awareness that we would want 5, 8, 10 years from now, here's our long-term list of all the stuff we want to accomplish. But it's even more important after you've thought about that long-term list to immediately switch down to very low altitude. What's the first realistic project we can do with high confidence that we'll have success? So you want to think in the back of your head, here's the long-term goal, but focus on deploying a very small, very high confidence first project only. Data structures are an important thing on data structures to make sure that you have left yourself room for data correlations you haven't thought of. If you try to make one table that contains all the information about a given part, then you're not leaving yourself the flexibility to correlate data that you haven't even thought of yet. It's much better to have smaller sets of data that get correlated with each other rather than one set of data that contains everything. And then the final thing I'll throw out here is it's important to consider agile project management. Agile project management allows us to start with basic concepts of what we're trying to achieve, but change our goals, change our scope, change our tactics, our tool sets as we go along. So as we analyze more and more data, as we learn more and more from the data, we need to make sure that we've worked with a tool set that allows us to change, and now we're going to focus on quality instead of availability, because it turned out that quality was our #1 problem. Now we're going to focus on grabbing data from other data systems instead of from PLCs, because it turned out that the important information was in a database instead of in the PLC. So working with tools that allow us to do agile project management allow us to change the scope and to adjust as we go along. And that's really all I had to talk about today. I appreciate your time.
Well, thanks, Jim and Thomas. Those were two cogent, detailed presentations, and we appreciate it. We look forward to seeing you in the live Q&A session immediately following. Be sure to have your questions ready. Thanks for joining us, and we hope the information provided suits your purposes.